Okay, good morning. So we have been discussing about multi-stage systems. In the previous lecture, we discussed about multi-compression system, and there we found that if we go with the flash chamber, then there could be practical limitation because of the presence of liquid and vapor mixture at the entry of the expansion valve. That's why instead of directly taking out saturated liquid from the flash chamber, what we did, we used a subcooler. Okay, and within the subcooler actually we decreased the temperature sufficiently below the saturated liquid temperature, so that we can always ensure that at the entry of expansion device we have actually we have what, pure liquid. Okay, however it resulted in a small amount of penalty. Okay, so what was the penalty? The penalty was that refrigeration effect has slightly decreased. Okay, then this is all about multi-compression system, and in all these systems our aim was that evaporator was operating at a single temperature condition. Okay, after that we shifted to some systems which are called as multi-evaporator system. So in case of multi-evaporator system, our requirement could be that one of the refrigerated space I need to maintain at some temperature TE1, and the other refrigerated space I need to maintain at some other temperature TE2. Okay, so whenever we saw that type of arrangement, and moreover it may so happen that this type of temperature requirement is well within the temperature limits of the single compressor system. Okay, so if it is within the limits of the single compressor system, for example, if I say my minus 30 degrees Celsius is the lowest evaporator temperature, say 5 degrees Celsius is the middle evaporator temperature, and 40 degrees Celsius is the condenser temperature. So now generally from minus 30 to 40 degrees Celsius range we operate with the help of a single compressor. When we go below minus 60, then we go for two compressors. Okay, so now though I have two evaporators, but still my condenser and the smallest evaporator temperature limit, that is well within the acceptable range for single compression system. Okay, so that's why in this system what we have done, we have used a single compressor, rather we have to use two different expansion devices in order to operate at two different evaporator temperatures. So that is what I explained in the previous lecture, that we have two expansion devices. So part of fluid is going through evaporator 2, part of the fluid is going through evaporator 1. However, at the inlet to the compressor, because we need to again mix these together, so we have to use a pressure reduction valve at the exit of the evaporator 2. Is this one clear? So this system we have done, and its thermodynamic analysis also we performed. We calculated the individual mass flow rates across each each evaporator, and we also estimated the total amount of work done required. So if one has to simply determine the COP, that will be nothing but RE1 plus RE2 divided by W. Is this one clear? Up to this things are fine. Now the point is, if I go, there can be two scenarios. One scenario could be, if I can go up to temperature of say minus 60, minus 70 or so, one evaporator is required at temperature close to minus 60, and other is required at say almost 5 degrees or 7 degrees, whatever may be the scenario. Okay, so in this case what will be happening? In this case I will be finding that this particular point 8, it will not stop over here, but it has to, because this evaporator is to be operated at further lower pressure. So I will be having some low pressure, and this will be further going down. So as long as we keep on decreasing the pressure of the lower evaporator, what will happen? If I just do the expansion from the same state, then throttling loss will keep on increasing. At the entry of the smallest evaporator, at the smallest temperature evaporator, we will be finding there will be presence of large amount of vapor medium. So this large amount of vapor medium will be of course having the two negative effect. One effect is vapor medium will be having very high specific volume. So it will try to have a large evaporator coil. Second thing is, if you have significant amount of vapor already in the tube, then there will be good amount of interfacial shear stress, which will lead to large pressure drop. And third thing is, vapor presence in the evaporator is not good, because ultimately it decreases the rate of heat transfer. At the same point of time, it does not contribute anything on the refrigerated load. Okay, because refrigerated load is majorly contributed by the conversion of liquid into vapor. Is this point clear? So that's why whenever I will be operating with the little bit large temperature limits of the smallest temperature evaporator to condenser evaporator, then in order to avoid all these issues, what we need to, and moreover, if this ratio is large, then using a single compressor for large pressure ratio will again be leading to large amount of work input and significant decrease in volumetric efficiency of the compressor, because volumetric efficiency of the compressor is proportional to the ratio of pressure across which it is working. So if pressure ratio is large, then volumetric efficiency decreases. Okay, and if it is pressure ratio is small, then volumetric efficiency increases. Now what we need to do then for multi-evaporator system also, I will be now having what? Multi-evaporator, but with what? Multi-compression. And let me include everything in this. So if I include everything in this, then I have to use a flash intercooler, water intercooler, and liquid subcooler. The most practical system I am actually trying to explain. Is this one clear? So now what typically will happen? I will be having a condenser. From the exit of the condenser, I will first have one expansion valve, and this expansion valve will supply refrigerant to evaporator 2. Then when I am supplying to the lower evaporator, instead of directly supplying, I will first use a flash chamber, and within the flash chamber I will be doing liquid subcooling. Okay, so for using a flash chamber, I have to use float type expansion valve. Here I will be having liquid, and at the top I will be having vapor. Then I will be taking remaining portion of the refrigerant, and this I will try to subcool. After subcooling, I will be using again an expansion valve, which will then go to evaporator 1. After evaporator 1, I will be having a compressor. Then I will be having a water intercooler. After water intercooler, flash intercooler. This is a flash intercooler. Fine. After that, the vapor which is coming from here and the vapor which is coming from evaporator 2, these will mix together, and finally I will be having next compressor, and then it will go to condenser. Is this one clear? Anyone is having any doubt about this? Please tell me. State 1, state 2, 3, 4A, 4B, let's say mixing forms state 4, then state 5, 6, here also it will be 6, everywhere it will be 6, here it will be 7, here it will be 8, and here it will be 9. All are clear with this point? Anyone is having any doubt about the system? Okay, so I do have now two evaporators, evaporator 2 and evaporator 1, and for the second lowest temperature stage, I have a flash intercooler, I have liquid subcooler, and I have a water intercooler. Is this not clear? Okay. Now what I need to do? Next task, I need to draw it on pH diagram. Okay, so on pH diagram, I will be having three pressure limits. Condenser pressure, PE2, second evaporator pressure, and first evaporator pressure. Now you tell me, what is at the exit of evaporator 1? Always it has to be a, under ideal condition, it has to be a saturated vapor state. So this is state 1, then 1 to 2 it will be compression process, then 2 to 3, what? Intercooling, water intercooling. 3 to 4A, it will be flash intercooling. Ideally, flash intercooling always results in which state? Saturated vapor state. So I will come to this point. This will be 4A. Then this is evaporator 2. At the exit of evaporator 2, I have 4B. Ideally, exit of evaporator should be saturated vapor. So it means 4B will also coincide on this. Okay. Now, if two states under same enthalpies are mixing together, then resultant enthalpy will also be same. So it means 0.4 will also be here. So this nothing but represents 0.4A, 4B, and 4. All 3 points are under ideal conditions coinciding on the saturated vapor state. Is this point clear? Then from 4 point, what I will be having? Compression. Then 5 to 6 I will be having condensation. Ideally the exit of condenser is always saturated liquid. Then 6 to 7 I have two expansion processes. One expansion is for entry to evaporator, and other expansion is for entry to flash chamber. Okay. So if you see 6 to 7, you have to mention that there are two expansion processes from 6 to 7. One expansion is entry to evaporator, so from 7 it will be entering to evaporator, and then ultimately it will be going to state 4. And other is entry to flash chamber, where some liquid and vapor will form. Vapor will again go to state 4 and liquid will remain within the flash chamber. Liquid is remaining within the flash chamber. Is this one clear? And that liquid is being used for two purposes. One is for intercooling of this vapor and other is for subcooling of this. Now the remaining refrigerant entered at state 6, and then at state 6 it is exchanging heat with the liquid which is at state 7. So 7 is at low temperature, 6 is at high temperature. There will be subcooling from 6 to 8. 6 to 8 is subcooling process. And then from 8 to 9 I have this long expansion process, which is for low temperature evaporator. Is this point clear? So this is a multi-evaporator, multi-compression system, because I am using two compressors, and ultimately in this system what I have liquid subcooler also, flash chamber also, water intercooler also. Okay. Okay, so Now can you find out the mass flow rate handled by low stage compressor and high stage compressor? Can you do this? First thing is very easy. What is the mass handled by low stage compressor? Only the mass passing through evaporator 1. So mass passing through evaporator 1 can be written as m dot E1 equal to refrigeration effect of evaporator 1 divided by H1 minus H9. Now the mass passing through evaporator 2 can be refrigerated effect of 2 load on the evaporator 2 divided by H, please tell me, H4B minus H7, and 4B is nothing but 4. So H4 minus H7. Is this point clear? But the mass handled by high stage compressor is not only sum of ME1 and ME2. Other than that, because of the flashing, there will be some vapor formation, and because of intercooling and subcooling, some liquid will be converting into vapor. So load on this high stage compressor is greater than ME1 plus ME2. Okay, so how much will be the total? How to determine? Let me draw a control volume. This is a control volume. Now you tell me what is happening in this control volume. Let us consider m dot 1 is the mass handled by low stage compressor and m dot 2 is the mass handled by high pressure compressor. Okay. So m dot 1 is entering with enthalpy H3. Is this one clear? Over here, what is the mass? This mass will be m dot 1 here to here. Again, this mass has also to be m dot 1. The mass which is coming after condenser has to be m dot 2, and this mass leaving has also to be m dot 2 out of the control volume. Okay. Now you tell me, only these are the mass interactions. So m dot, please tell me, m dot 1 is coming with enthalpy H3, leaving with enthalpy H8. M dot 2 is leaving with enthalpy, coming with enthalpy H6. So m dot 2 will be equal to m dot 1 into H3 minus H8 divided by H4 minus H6. What is H3 minus H8? H3 minus H8 is this one. This is 0.3. This is 0.3. So it is H3 minus and H4 minus H6. This is 0.4. This is 6. So now H3 minus H8 is greater than H4 minus H6. It means m dot 2 will be greater than m dot 1. Few more things. M dot 1 will always be equal to m dot E1. All are correct with this? Agreeing to this? Okay, mass handled by this compressor will be nothing but the mass flowing through evaporator 1. And m dot 2 can be written as m dot 1 which is this mass, plus m dot E2, which is this mass, plus m dot dash, which is forming vapor mass forming within the flash chamber because of flashing, phase change, etc. Okay, total mass which is coming out of this. So it will be m dot 1 plus m dot m dot dash, where m dot dash is the total mass of saturated vapor because of flashing, intercooling and subcooling. Okay, that is coming out of the flash chamber. So from here I can say that the total mass which will be forming, that can be written as m dot 2 minus m dot 1 minus m dot of E2. One important relation. So this is the mass of vapor which is forming within the flash chamber, and it is forming because of three processes. One is because of flashing, other is because of intercooling and subcooling. Is this one clear? Now what will be the work done? Net amount of work done will be m dot 1 into H2 minus H1 plus H5 minus H4. So if you have to calculate the COP of the system, then COP of the system will be what? M dot E1 into H1 minus H9, m dot E2 into H4 minus H7, m dot 1, let me write m dot E1 only, is this one clear? So this is the COP of the system. Anyone is having any doubt about this? So if you recall, whatever the remaining things we need to do, the remaining analysis, that we will try to see with the help of numerical problems. Okay. So have you seen on Moodle portal, I have already posted the refrigeration tables, thermodynamic property tables. Okay, so particularly for different refrigerants, you try to bring these tables in the next class. In the next class, we will do numerical problems. Today, we will try to see another category of multi-stage systems, which are called as cascade systems. Okay. Before going to cascade systems, first we will try to list down some of the limitations of the multi-stage systems and the need for the cascade systems. Okay. So it has been very well established practically that if we operate within minus 30 degrees Celsius to condenser temperature, which is the usually the ambient temperature, then we can operate with the help of a single stage compressor. Then if I operate with minus 60 degrees Celsius to ambient temperature, then we have to go for two-stage compression, and if I go from say somewhere minus 100 degrees Celsius to ambient, then we go for three-stage compression. Now thermodynamically, if I have to go below that, because there are many applications, for example liquefaction of gases, etc., where we have to even go to temperatures as low as minus 200 degrees Celsius. Okay. So under these scenarios, thermodynamically always, if I just keep on increasing the stages, thermodynamically my system will be becoming more and more efficient. Okay. However, there is practical limitation that below 3 stages we don't go generally. What are the reasons? The reasons are, if you are keep on increasing the stages, ultimately the cost of the compressor system is increasing, you need to keep on using more and more compressors. So initial capital cost will be more. Other than that, whenever you are operating some system in very extremely large pressure conditions, one is operating at very low pressure, other is operating at very high pressure, then we will be having actually issues of sizing. So particularly if you keep on decreasing the pressure, what will happen? If I keep on decreasing the pressure, what will happen? Specific volume of the fluid will keep on increasing. So if specific volume is keep on increasing, then the volumetric flow rate, mass flow rate across the compressor will decrease. So it means that in order to achieve the significant mass flow rate, you have to take a large system. All are clear to this point? So one is that issue. So you will be having large system, it means the capital investment will be huge. Other than that, if you are having more and more components which are leading to wear and tear, because if you are talking about compression system, then compression will be having significant wear and tear because of the reciprocating motion between the piston and the cylinder. So in these scenarios, the maintenance cost of that system will also be high. So when my operating cost, like maintenance cost and the capital cost, is becoming significant in comparison to the thermodynamic benefit which what we would get in terms of improved COP, then these systems are not actually feasible. Okay, so that's why generally we go only for 3 stages. Now let us come to the second aspect. Second aspect is that my application is not always limited to minus 100 degrees Celsius only. I may have even go to minus 200 degrees Celsius. So if I go to minus 200 degrees Celsius, one immediate point I have told you that compressor size will be increasing. You have to use a large size compressor. Second important issue is refrigerants are typically classified in two categories. Few are called as high pressure refrigerants and second class of refrigerant is which are called as low pressure refrigerants. What it mean? It mean that the refrigerants whose boiling point is close to minus 40 degrees Celsius, okay, at ambient pressure condition, minus 40 or more, these are called as high pressure refrigerants. And the refrigerants whose boiling point, normal boiling point is say minus 100 or even smaller at ambient pressure, these are called as low pressure refrigerant. What it means? It simply means that if your condenser you need to, your evaporator you need to operate at minus 30 or minus 20 degrees Celsius, this particular, the evaporator of this high pressure refrigerant will be operating at pressure greater than the ambient pressure. Is this point clear? See, if the boiling point of a refrigerant is minus 40 degrees Celsius at ambient pressure and evaporator of using this refrigerant, evaporator is to be operated at minus 20 degrees Celsius. What it means? It means that boiling point has to be raised. In order to raise the boiling point, you have to increase the pressure. So it means evaporator of this type of refrigerant will be operating always at pressure above than the ambient pressure. That's why we call these as high pressure refrigerants. On the other hand, if I have a refrigerant whose boiling temperature is minus 100 degrees Celsius. Now, what I need to do? If I need to operate it at low temperature, because my aim is to go below. Okay. So if I think I explained you wrong. Here I made a mistake. Okay. So boiling point is minus 40 degrees Celsius. If I am going to minus 20, what I am doing? I'm decreasing boiling point or increasing boiling point? Please tell me. Increasing boiling point. Okay, so if it has to work at -20, of course pressure will be increasing. But if the same refrigerant is to be used inside a evaporator at -100 degrees Celsius, then what will happen? We have to decrease the pressure, and this pressure will be becoming then less than the ambient pressure. Okay, so whenever your evaporator pressure is less than the ambient pressure, in that scenario what will be happening? There will be significant chances of, if a small minor leakage is there in the system, air will enter into the evaporator coil, and air is a non-condensable gas. So being a non-condensable gas, it will decrease the volumetric efficiency of the system. At the same point of time, it will not participate in carrying the heat from liquid to vapor, and air will try to decrease the rate of heat transfer also, because the thermal conductivity of air will be very less in comparison to the corresponding liquid refrigerant. Is this point clear? So if we have to use high pressure refrigerants for very low temperature conditions, then other than the larger size of the compressor, their evaporator has to be maintained always at lesser pressure than the ambient pressure, and whenever we operate at lesser pressure than ambient pressure, then chances of leakages are more. However, presently you can say that we have the hermetically sealed compressor technology. Okay, so what is a hermetically sealed compressor? So right now if you see your fridge, at the back side of the fridge there is a black colored small chamber. So that black colored chamber, nothing but it contains the compressor. From that chamber only two pipes comes out. One pipe is for inlet, other is for exit, and there is one small tubing which is for the power connection. Okay, so it means that there can be two type of compressor. One is a fully open type of compressor. So open type of compressor, like you have seen in your laboratory also. So in your lab, what do you see? There is a tank at the bottom, then there is a compressor like this V-shaped compressor, and there is a pulley and belt which is connected to the motor. This type of compressor is called as open type compressor. But if you have a compressor where your this piston cylinder arrangement and motor, everything is packed inside a vessel, that is called as hermetically sealed compressor. Okay, so hermetically sealed compressors are having advantage that the chances of leakages in these compressors are actually very, very less. So one can say that even though my pressure is less than ambient pressure, I can go for the hermetically sealed compressor. So the disadvantage is that, one, there can be leakage into the evaporator coil, and other disadvantage is that typically whenever your compressor is completely sealed inside a vessel, then what we do, the cooling of, generally compressor require cooling. Okay, then the cooling of compressor, what will be happening? Cooling of compressor is generally done with the help of refrigerant which is flowing over the compressor. Okay, so in a hermetically sealed compressor, what will be happening, because the mass flow rate of the refrigerant will be decreasing significantly, it will not be able to do effective cooling of the compressor, and there will be chances of overheating of the compressor and decrease in its overall life. Is this point clear? So that's why we cannot use hermetically sealed compressors under such conditions. So that's why, in order to avoid the entry of air into my refrigerating circuit, we have to use some refrigerants which have low boiling point at the desired temperature conditions. Okay, so this type of refrigerants are called as low pressure refrigerants. Refrigerants such as ammonia, R12, R22, R502, R134A, all these refrigerants are comes under the category of high pressure refrigerants. Whereas the refrigerants such as R13, R14, R23, etc., these comes in the category of low pressure refrigerants. Is this one clear? Sorry? किसकी? Okay, so the disadvantage is that if you use high pressure refrigerant whose boiling point at minus 40 degrees Celsius is ambient, if you operate it at minus 100 degrees Celsius, you have to decrease the pressure. So when the pressure goes below the ambient pressure, there will be chances of leakage of air into the circuit. If air enters into the circuit, it's a non-condensable gas, it will decrease the mass flow rate of the refrigerant and it will also decrease the rate of heat transfer in the evaporator and the compressor. The other point is we cannot use hermetically sealed compressor under these scenarios, because whenever pressure will decrease significantly, the specific volume of the refrigerant will increase. So increasing specific volume means it decreases the mass flow rate across a compressor. So you have to use large capacity compressor. Is this one clear? All are clear with this point? So these disadvantages can be overcome if we use combination of high pressure and low pressure refrigerants. So what we can do, in the multi-stage compression systems, we were having high pressure compressor and low pressure compressors, but working fluid in both the compressors was same. Now what we will be doing for achieving the extremely low temperatures, we will be using one simple standard refrigeration circuit for low temperature condition, other refrigerant circuit for high temperature conditions, and the condenser of the low temperature refrigerating circuit will act as evaporator to the high temperature refrigerator. Is this point clear? So this is how we will be actually clubbing the system. So we call this type of system as cascade refrigeration systems. Okay, so what I'll be having a condenser which obviously will be operating at the ambient conditions. Then I'll have one expansion valve. After the expansion valve, over here I will be having one intermediate heat exchanger, and then I will be having compressor. So this is the high temperature cycle. Then another I will be having a low temperature cycle. This will be evaporator. Now here what will be happening? Heat will be transferring from this to this, and this will happen inside a heat exchanger. This particular heat exchanger is called as cascade condenser. Okay, and evaporator generally operates at extremely low temperature, even lesser than minus 100 degrees Celsius, because up to minus 100 degrees Celsius we can simply go with the 3-stage system. Okay, so less than minus 100 degrees Celsius will be my evaporator. Then in this I will be using a low pressure refrigerant, so that the pressure within the entire circuit is always greater than the ambient pressure. And in the top one I will be using high pressure refrigerant. Now in both the circuits, pressure will always be greater than the ambient pressure. So it means we are not decreasing the specific volume to such a we are not increasing the specific volume to such a higher value so that it can affect the mass flow rate across the compressor. Is this point clear? So this type of system is called as cascade refrigeration system. Now one important thing you have to note down, that the temperature of this system, temperature of this working fluid has to be greater in comparison to temperature of this top working fluid. Is this point clear? Let me repeat it again. If this is condenser So this is nothing but TCLT. TCLT means low temperature circuit condenser, and it is evaporator for HT. So TEHT, it means evaporator of the high temperature system. Now the condenser of the low temperature system should have greater temperature in comparison to temperature of the evaporator temperature of the high stage. Then only heat will be transferring from this to this. So it means that cascade systems are having inherent irreversibility. Is this point clear? So generally what we do, even whenever we consider the standard VCRS cycle, we say that we are having all internally reversible processes. But over here, this process will not be internally reversible because we have finite temperature difference between the two sides. So whenever there is a finite temperature difference, there is irreversibility. Okay. So this process is basically irreversible process. So it means that if there is irreversibility, it means thermodynamically this process cannot be more efficient than the multi-stage system, where all processes are internally reversible. Is this point clear? So thermodynamically this cannot be better. Now what I will be having? Of course, whenever we deal with these systems, what we need to do? We need to draw the pH diagram. So now I will be having two domes, and in two domes, one interesting point you can note down. This is your one critical point, this is your other critical point. So usually the critical temperature of the low pressure refrigerant is significantly smaller in comparison to critical temperature of the high stage. So if critical temperature is very low, it means that this low pressure refrigerant cannot be used up to the ambient temperature conditions, because corresponding to ambient temperature, it may so happen that it will be crossing its critical stage. So if it is crossing its critical stage, it will always be remaining in the vapor phase. It will not come back into the liquid phase. Is this point clear? All are clear with this point? Okay, so now what I will be having? Let me do one thing. Let me name the cycle. So say lower cycle I am naming as ABCD and the top cycle I am naming as 1, 2, 3, 4. So what is this? This is point 1. Top cycle is 1, 2, 3, 4. Point 1. 2, 3 and 4. Fine. What else I will be getting? A to B, B to C and C to. So this is how you will be having the overlapping cycles. All are clear with this point? Now refrigerating load is only acting at the bottom space, okay, because that is the desired temperature which we want to cool. So I can say that refrigerating load can be written in terms of mass flow rate of LT, low temperature cycle, into HA minus HD. From here you can calculate the mass flow rate of LT. Now, what will be mass flow rate of HT? How to calculate? LT is entering into this cascade condenser and changing enthalpy from B to C. So m dot LT into HB minus HC. Under the steady state condition, this entire heat should go to the top one. So say top one is having mass flow rate of m dot HT. Then m dot HT into enthalpy is changing from 4 to 1. So H1 minus. This is after applying energy balance across the cascade condenser. All are clear? So from here I can simply calculate m dot HT equal to m dot LT into HB minus HC divided by H1 minus H1. What is clear? What will be COP? Refrigeration effect, which is m dot LT into HA minus HD divided by work done, which is m dot LT into HB minus HA plus m dot HT, which can be written as m dot LT into HB minus HC divided by H1 minus H4 into H2 minus H1. LT will cancel out. What I will be getting? COP of the system will be HA minus HD divided by Is this point clear? All are clear with this point? Anyone is having any doubt? So right now whatever I have discussed, it's a simple cascade system in which both the LT and the HT cycles are actually standard cycles. Now it may so happen that you are operating in a temperature limit, say this is operating at minus 150 degrees Celsius and it is going up to say minus 40 degrees Celsius. Then the another cycle has to be operated in between somewhere close to minus 50 degrees Celsius to, or say it is only going up to minus 80. Then another cycle has to be operated from minus 90 degrees Celsius to what? Ambient, close to 40 degrees Celsius. Okay, so in this case now you see bottom cycle is fine, minus 150 to minus 80, but top cycle is having now temperature limits from minus 90 to 40. So it means top cycle cannot be operated in a single stage. So now you will be having the cascade system, but in this cascade system, in the top cycle you have to use two compressors. Is this point clear? So it means that depending upon the requirements of the temperature, any cycle LT or HT can have multi-compression systems. Is this point clear? And whenever there will be multi-compression, of course, there will be what? If there is multi-compression, then there will be always flash chamber, liquid subcooler, etc. All the components will be coming into picture. Okay. Okay. Now one important point is, I told you that we have to operate at some intermediate temperature. In case of multi-compression systems, we have determined the optimum value of the intermediate pressure at which we should operate. Okay. Now we need to estimate the optimum value of this intermediate temperature at which we should operate. Now how to estimate this optimum value? What should be the intermediate temperature at which my cascade condenser should operate. So basically, I told you one thing, the condenser LT and evaporator HT. So it means cascade condenser is not operating at a single temperature. This temperature is large, this temperature is small. So ultimately, the intermediate temperature of cascade condenser we simply define as the arithmetic mean of condenser of LT plus evaporator of HT. So this is called as intermediate temperature. But how to determine the value of this intermediate temperature? What should be the optimum temperature we should choose for using the cascade cycle? How we can decide this? That is one point, and another point is in the cascade we will be having some delta T. Delta T will be temperature difference. This delta T will be nothing but Tc LT minus Te of HT. And from here I can simply say that Ti will be equal to Tc LT minus delta T by 2, and Ti can also be TeHT plus delta T by 2. Is it correct? Simple mathematics. If this difference is delta T, this is mean, I can write Ti as TCLT minus delta T by 2 and this TeHT plus delta T, right? Simple mathematics. Now, whenever we have to define some optimum condition, always we go where? Always we go to Carnot cycle. And from Carnot cycle we try to make some assumption. Okay. So, if I use a cascade Carnot cycle, for cascade Carnot cycle I will be having this type of situation. This will be my high temperature Carnot cycle on TS diagram. Okay. And if I am talking about the 100% efficient system, in 100% efficient system there should not be any irreversibility. Okay. So it means that the intermediate temperature can be overlapped for condenser of LT and evaporator of HT. So my second cycle can simply start from here and it can be something like this. Okay, all are clear with this point? Anyone is having any doubt, please tell me. So this is nothing but the reverse Carnot cascade cycle with zero temperature difference in cascade condenser. All are agreed to this point? Now, if this is the situation, then this will be evaporator temperature, this will be intermediate temperature Ti, and this will be condenser temperature Tc. All of you agree to this? Now, what will be the COP of lower cycle? COP of RCLT will be Te by Ti minus Te, and COP of RCHT will be Ti divided by Tc minus. All of you agree to this? Is this correct? Now, let us consider, if you increase Ti, what will happen? If you increase Ti, COP of RCHT will, if I increase Ti, then COP of RCHT will increase and COP of RCLT will decrease. Is this one clear or not? If I increase TI, what will happen? This COP will increase and this COP will decrease. If I decrease TI, then COP of RCHT will decrease and COP of RCLT will increase. So it means that TI will be having some optimum value where both the COPs can be equal, and if I deviate from that value either in positive direction or in negative direction, then one COP will increase and other COP will decrease. So the most ideal situation to us is that we should reach to a condition where both the COPs of LT and HT are same. So let me equate both the COPs. For ideal situation, COP of RCLT should be equal to COP of RCHT. You equate it. Now you see what you will be getting. Please calculate what you will be getting. TETC minus TETI equal to TI square minus TETI. TETI will cancel and intermediate temperature you will be getting TE into TC square. So it means under the ideal condition, if we do not have any irreversibility, it means cascade condenser is operating with zero temperature difference, then my TI has to be equal to square root of geometric mean of evaporator and the condenser. Okay, but this will not be the situation. What will be situation? In actual condition, what will happen? There will be some difference of delta T by plus delta T by 2 minus delta T by 2. So if I take actual condition and then equate COP, what I will be getting? Please tell me, for LT cycle, what will be COP? TE divided by TI. What is condenser temperature of LT? TI plus delta T by 2 minus TP. Is this one clear? And this has to be equal to the COP of the top cycle. So for top cycle, evaporator has to operate at TI minus delta T by 2 upon condenser temperature minus evaporator temperature. How I have written this? Is it clear to all? It's very simple. In cascade condenser, you have two working fluid. If Ti is the mean temperature, this working fluid is at temperature of Ti plus delta T by 2 and this is at Ti minus delta T by 2, and this is acting as evaporator for the high temperature cycle. So evaporator temperature by condenser minus evaporator, and in this case it is acting as a condenser to the low temperature cycle. So evaporator divided by condenser minus. Okay, from this we will be getting that Ti is equal to square root of, you can solve it mathematically, I am giving you now the final result, delta T square by 8 into square root of Te into Tc. So what is this delta T? Delta T is the temperature difference between the two streams which are participating in the cascade condenser. If delta T is large, size of heat exchanger will be small. If delta T is small, size of heat exchanger will be large. if delta T is large, the thermodynamically cycle will be less efficient. If delta T is small, thermodynamically cycle will be more efficient. So we have to choose the value of delta T which gives thermodynamically also good efficiency. At the same point of time, the size of the system is also cost effective. Okay, so that is how delta T is linked to the selection of the intermediate temperature and to the size and the performance of the system. Is this point clear? So probably with this our discussion on multi-staging is over. Theoretical discussion. In the next class we will try to see one or two numerical problems, and after this we will refer to next unit.